like to discuss some of the mechanisms that insects use to fly. Much of this information I have taken from a video that you can watch online. It's by Michael Dixonson, and he's a professor at Caltech. He has made enormous contributions to sorting out just how insects are managed to fly. But before, and I'll show you a clip or two from this video, but the link is there, and I really recommend you watch it. It's about half an hour, but it's wonderful. And before I show you some of those clips and discuss it, I wanted to make sure that, just to remind you of some background information. Just to review some background information, we talked a little bit about Bernoulli's theorem, but I want to go over it in a little more detail. So this comes from the conservation of energy. And basically what it's saying is that the sum of the kinetic energy and the potential energy is a constant. And this only holds true for ideal fluids that don't have any viscosity. But it turns out it's pretty useful. So that might seem very limiting, but in fact it's pretty useful. So the kinetic energy of a given volume of a fluid that's moving, that's flowing, is simply 1/2 mv squared, where m is the mass and v is the velocity. The potential energy is the pressure multiplied by that volume, plus a gravitational potential energy, which is going to be the mass of that volume, and however the Earth's gravitational multiplied by the Earth's gravitational acceleration multiplied by the height. So when you're working with a continuum like a fluid, it's not that handy to work with mass, and the easier way to deal with these equations is instead work with density, and you can accomplish that by simply multiplying both sides of that equation by the density divided by the mass, and that gives you a new constant, right? It's not the same constant, but still the equation's true. So now we have the pressure, so this is the static pressure, plus 1/2 rho v squared, where rho is the density of the fluid, v the velocity squared, or v this velocity, plus the density times gravitational acceleration times the height. The term 1/2 rho v squared, that's known as the dynamic pressure. Okay, so that's coming from the kinetic energy. And if the difference in height between one way to get around the problem with these constants, or having to worry about the constants, is to look at differentials. So the pressure at one point compared to another, or the velocity at one point and compared to another. So that gets rid of the need to actually measure the constant. If the height difference between point 1 and point 2 isn't very large, then you can ignore the height, that gravitational potential term. So if you're looking at water, falling down a long pipe, you can't ignore that. But if you're looking at something like an insect wing, the height between the top and the bottom is small and it's negligible, so that can be ignored. So then you're left with this equation of the pressure differential is equal to the density of the fluid divided by 2 multiplied by the quantity of the velocity, the difference between the velocity squared terms. And that's quite important, that velocity squared. This is not a linear relationship. The pressure difference is related to a velocity squared term. It's a power function. When a sphere or a cylinder is spinning in a viscous fluid, there's a boundary layer, and that spin will cause a circular flow. If that sphere is also translating, so if it's like a baseball that is thrown through the air but is also spinning, or a golf ball, then in this case the spin is counterclockwise and the flow is coming from the right, the spin, then the motion that's induced by the spin is actually increasing the speed of the flow on the downward side of this ball and decreasing it on the upward. And so where those streamlines are closer together, there'll be less pressure and there's a downward force. If the ball were spinning counterclockwise instead of clockwise, the streamlines would be closer together on the top of the ball and there would be an upward force. This is known as the Magnus effect, and this is very important in insect wings and the way that they maneuver their wings. This schematic illustrates a section of an airfoil. Let's say it's a cross-section of an insect wing. And the air is moving faster. There's a higher velocity of flow on the top of that wing than on the bottom because it's tilted up and there's an angle of attack relative to the angle of the oncoming wind. And so since there's higher velocity, then there's also lower pressure. So there's lift being generated. That foil is being pulled up. Because there's lower pressure on the top, that actually tends to sort of suck molecules around from the bottom. They want to join in. There's a result of the higher pressure on the bottom actually pushing, or the lower pressure sucking. That differential moves some of these molecules around. And that is true the whole bottom length of this wing. So this movement counter to the direction of airflow, this is called circulation. And the flow, the net flow around this wing, this circulation around, or the net flow around the wing like this, is related to the lift that's generated by the Kutta-Joukowski theorem. So the lift is equal to the density of the fluid, the velocity, and then this volume or this net flow around the wing. I want to show you a movie that where I think you can see, if you look closely, you can see this circulation occurring.
Vein. The circulation of the starting vortex, seen here, is matched by an equal and opposite lift-producing circulation around the foil. The fact that circulation actually occurs around the foil is seen from the vortices that detach as the foil is stopped. A lift coefficient can be written for a vane of length L and chord C as the lifting force per unit vane area in its ratio to the stagnation pressure. According to the circulation theory of lift, this coefficient is proportional to the relative circulation, which in turn is proportional to the sine of the angle of attack of the vane. A plot of the measured lift coefficient against angle of attack shows good agreement with the circulation theory at small angles, but a great deviation at high angles as the phenomenon known as stall occurs. By means of smoke filaments, the gradual development of stall, or leading edge separation, is readily seen from the change in flow pattern around this symmetrical vane, as its angle of attack is continuously increased. Piezometers at the numbered point vane. The circulation of the starting vortex, seen here, is matched by an equal and opposite lift-producing circulation around the foil. The fact that circulation actually occurs around the foil is seen from the vortices that detach as the foil is stopped. A lift coefficient can be...
So the effect of having this high pressure air from the bottom wrap around to the top of the airfoil doesn't just happen on the front of the foil, it also happens on the very tips of the wings. And that's illustrated here. So you can see over in the right-hand corner, the very tip of the wing, you have the air, the high pressure air wrapping around over onto the top of the wing. And then this sets up a vortex. So the middle picture with blue is showing you this wingtip vortex. And then the image ahead of it, if you can see the tips of those arrows, also shows you the movement of air from underneath the wing, around the ends of the wing, and over up on top. And then these other illustrations or these other photos are just showing the actual wingtip vortex that is left behind some planes. And this can be a significant source of drag. Now, one way to study the forces acting on a wing is to divide that wing up into sections. And that is illustrated here. So this is a chord or a section that with the head of the chord marked as a little ball on the leading edge of the wing. And then one can draw a force diagram. So what forces are acting on just this one section of the wing. And that's illustrated below. So if the wing is sweeping forward, the leading edge of the wing is this ball again, and is sweeping forward with an angle of attack of alpha, there's a force generated that's more or less perpendicular to that wing. And the force is a combination of the lift, that's lifting the wing up, but also drag. So the air is resisting the bee swinging its wing forward. So that's a drag component. And if one analyzes the lift and force generated throughout an entire stroke, and this was done originally by Torkel Weiss Vogue, and then later by Charlie Ellington. And what they found was that, there's something really strange going on, because the lift that you calculate isn't sufficient to actually hold the insect in the air. So something was going on that they didn't understand. You can't use simply this conventional way to analyze lift and drag and understand how insects fly. So insects should not be able to fly by the theory that they understood. This is when Michael sort of came into the picture. There was this mystery, and he played a big role in solving it. And one of the things he did was, well, first of all, let me go back to explaining the ratio of the lift and drag. One way these coefficients are obtained by measurement. So you put like a wing in a wind tunnel or a hydrofoil or airfoil or in a flume, and measure for a given angle of attack the lift forces and the drag forces. And then you can get these coefficients, and that's plotted over here. So for an angle of attack, there's a lift coefficient, which is CL, C sub L, and there's a drag coefficient. These little strain gauges that are attached to the wing that measure it. And then change the angle of attack, etc., and you get these plots. A common way to plot this is to plot the lift coefficient over the drag with respect to the drag. So the drag coefficients on the x-axis and the lift coefficients on the right axis. And this is an aerodynamic polar. This was discussed in a little bit in the movie I just showed you. A straight line through the origin to the point that is tangent on this curve is where your airfoil will have the best lift to drag ratio. So this slide shows data collected by Ellington, putting wings into flight tunnels and measuring the lift coefficient and the drag coefficient and making this polar aerodynamic graph. And the pink bar that's right up at 2 is the range of the lift to drag needed in order for the insects to support their own body mass, their weight. And you can see that none of these insects theoretically could generate enough lift to fly. The approach that Michael Dickinson used was to make dynamically similar insect wings. So that it's hard to study an insect wing because it's so small. But if you can scale it up, it's much easier to put force measure instruments on it, etc. And he realized that's very common when you're studying fluid dynamics to use this concept of dynamic similarity. So if the Reynolds number is the same, the behavior will be the same. If you have a big Boeing 747 and you want to study it, you can make a small model. Instead of trying to build a huge wind tunnel, you can make a small model and then change the velocity or change the viscosity of the fluid that you're studying. Maybe put it in water instead of air, or maybe, it's just that ratio of the characteristic length multiplied by the velocity of the flow multiplied by the density divided by the viscosity. So as long as the Reynolds number is the same, the behavior will be the same. So he made a big insect wing, which is shown here to the left, and then filmed the flow over this wing. And I'm going to show you some stills of what he found, and then I'll show you a little clip of the movie that he has online. So this shows this mechanical wing, this enlarged mechanical wing, and the cord is illustrated with the red. The knob at the end is the leading edge, and then the cord is the red line. And what you're going to see is this is moved directly forward, so that arrow marks the direction of motion. There's going to be fluid move. Really, some of it's coming from underneath, right around where the leading edge is, and it's going to form a vortex on that leading edge. And you're going to see a trailing edge vortex form also. So this is a little bit later in time, and I have superimposed the red indication of the cord. And you can start to see a little bit more swirl, and then this is a little bit later in time. So now you're really starting to see the development of that leading edge vortex. A little bit later, even in time. It's cleared away from the lettering, so now it's become very clear. You can see both the leading edge, hopefully the leading edge, and this trailing edge vortex starting to form. And then it's detached at this point. It's that the leading edge vortex is actually pulled away, or mainly pulled away.
I'd like to focus on is our insects, which are my favorite creatures, because I think in many ways they excel in aerodynamics, flight control, as is demonstrated by this high-speed video sequence that you're seeing, which was shot at 7,500 frames per second in infrared lighting. It shows two flies on a collision course, and the entire sequence lasted only 200 milliseconds, which is approximately a fraction of a human eye blink. The two flies were on a collision course, but they saw each other with their eyes and were able to initiate evasive maneuvers to keep from crashing. It's just such types of behaviors that have inspired me throughout my career and have allowed me to focus 30 years or more of research on the problem of insect flight. It's also worth mentioning that insects are unique to operate at the highest lift-to-drag ratio. Now, before going forward with why it's hard to explain how insects can fly, I want to introduce a slightly different way of deriving the lift that's generated by a wing. So imagine I put a wing in an airflow, and that airflow is going to be distorted by the presence of the wing, because obviously the air can't flow directly through the wing. And the way it's distorted means that the flow of air on top of the wing actually has to travel over a longer distance than the flow of air beneath the wing. And as a consequence, of this velocity difference, there's a slight pressure difference. This is a phenomenon known as the Bernoulli effect, which explains why wings are actually sucked upwards. But another way of thinking about this is because there's a differential in velocity on the top surface of the wing relative to the bottom surface of the wing, it's as if there's a net circular flow around the wing. And this is what introduces a very, very important topic, which is called circulation, which measures this net flow of air around a wing. And it turns out that one of the most important equations in aeronautics is the so-called Kutta-Joukowski theorem that says that the amount of lift generated by any tiny section of the wing is proportional to circulations, proportional to sort of how big a velocity differential the wing can create. And we'll see that circulation plays a big role in our understanding of how insects fly. Okay, so let's get back to trying to explain what the basic problem is. Well, back in the 60s, 70s, and 80s, researchers had some of the first access to high-speed movies and now high-speed videos of flying flies. And yes, indeed, this is a fly that's pooping as it's hovering there in the air, answering the questions, do flies poop when they fly? And the answer is absolutely yes. But the main reason I'm showing you this is to get a sense that it would be possible to take a high-speed movie or video of an insect and determine what the motion of the wing is at each instant in time. One could then take such a data and try to reconstruct how much force I was flying through the air. So what I'm going to show you is the actual movie that Carl Gutz and I took. And what you're going to see is a wing, which is shown here. I'm just pointing out where it's going to appear with the red line. This wing is going to move through the fluid at a Reynolds number the same as a fruit fly wing and at a very high angle of attack. And what I want you to notice is a swirling structure on the top of the wing, which is something we call a leading edge vortex, which turns out to be really in many ways the secret to insect flight because it generates so much circulation. So I'll play the video. And there you can see the wing, and you can see this very large vortex on the top surface, this leading edge vortex. And I'll play it one more time. So to get a quantitative sense of what's going on, what I'd like to show you, since this time, we've generated lots and lots and lots of evidence showing the importance of leading edge vortices. And this has mostly been done by creating more and more complicated robots. So what I'm showing you here are movies of various versions of what we call in my laboratory RoboFly, which flaps its wings in a giant 2 metric ton tank of mineral oil, instrumented in such a way that we can measure the forces and flows that it generates very, very accurately. So we know from these sorts of experiments, before I get there, let me just show you some of these measurements of the leading edge vortex and visualizations that have come from such experiments. So I'm showing you in this one movie what you would see if your eyeball was staring down the axis of the wing as the wing was flapping back and forth. And you can see this swirling structure that develops right at the leading edge. In this animation immediately to my right, this is actually a simulated flow from a computer model done by a former student in the lab, Sean Humbert. And you can see this leading edge vortex, an important fact about it. And that's the fact that the leading edge vortex develops on one surface of the wing then flips over, and the leading edge vortex develops on the other surface. So the insect actually is sweeping its wing back and forth, and every time it flips over, it generates a new leading edge vortex, which is producing this high circulation and producing these very large forces. So leading edge vortices seem to be the real reason that insects can fly. And since this early work on insect flight, leading edge vortices have been found in a variety of different organisms. They're used by swifts, as swifts can glide quickly through the air. They're generated by bats when bats are hovering. They're produced even by the tails of fish as fish are flapping back and forth. They're flapping their tails back and forth very quickly. Leading edge vortices are even generated by plant seeds, such as maple seeds when they swirl to the ground. So this seems to be a common trick that evolution has found again and again to produce very, very large forces. Now, in the next couple of movies, what I'd like to show you is really why we got this wrong for so long. And it has to do with exactly how an insect flaps its wing. So an insect doesn't flap its wing or move its wing like an airplane. That is, it doesn't simply translate through the air, but rather it rotates more like the wing or the fan blade of a helicopter. So here you see a wing of RoboFly translating through an oil tank, and this was a movie taken by David Lentink when he was in my laboratory. And you can see the leading edge vortex develop as the wing starts to move, but then the vortex gets shed quickly as it moves through. This is the mechanism, or rather the process, that we call stall. However, you take that exact same wing and you move it in a different way. You revolve the wing as it does would revolve on a helicopter, and then you see a nice stable leading edge vortex that is not shed as long as the wing continues to revolve. So really one of the key things is the fact that insects revolve their wings rather than translating them. So to just give a summary of that, if you take a wing and translate it through the air as it would on an airplane, what you see is a leading edge vortex that's very unstable and quickly sheds. If you take that same wing and revolve it as it would on the rotor of a helicopter, what you see is a leading edge vortex that stays attached for the duration of motion. So we should really think about insects as being like little tiny helicopters, but instead of revolving their wings continuously, they revolve their wing in one direction, flip it over, revolve it back, flip it over, revolve it back, and so forth. Now, that's not the only thing that's going on with insect flight. This mechanism, sometimes called delayed stall, involving the leading edge vortex. This is certainly very important in the middle of each stroke as the insect is flapping its wing. But because an insect has to actually revolve its wings, stop its wings, and move in the other direction, there are some opportunities for other interesting aerodynamic mechanisms. And one of them is something we call rotational lift, because the wing actually has to flip over before it begins translating the other direction. And that process of flipping over is able to generate even higher forces. The leading edge vortex can even get larger. And these forces are somewhat analogous to the forces that are generated when a baseball or tennis ball spins as it moves through the air. In addition, as the wing stops and starts to move in the opposite direction, it intercepts the wake generated by the previous stroke. And if it does so in an efficient way, it's actually able to extract energy from the wake, something we call wake capture. And it turns out that for certain insects, and particularly insects that have very, very, very short strokes, so they're basically always flipping the wing over, that these so-called rotational mechanisms play a large role. For example, in this honeybee, and you can see just how brief its strokes are before it flips over. And honeybees make use of these rotational forces as they fly. So the last thing I want to say is that as you imagine an insect flying through the air, and this is going to be important when we consider topics such as power and control, but the insect can vary the way the wing is moving. It can modify the angle of attack. It can change slightly the velocity from one stroke to the next. And as a consequence, it can vary the direction of the forces that are being produced by the stroke. So it can, for example, fly backwards or forwards via subtle modifications in the way that it's moving its forces, whether the way that it's moving its wings through the stroke.